So we've seen that for static fluids, the pressure gradient dPz is equal to minus rho g in an unmoving static fluid. And that means we can integrate that and show that P2 minus P1 equals rho g Z1 minus Z2 if rho and g are constant. So we studied a problem last time where we were looking at water, and water does have a very constant rho, a very constant density, pretty much regardless of situation. Liquids are very are incompressible substances, essentially, almost perfectly. So water has a very constant density, but air, of course, does not have a constant density. We know that air can be compressed. So it's reasonable to wonder when we can treat air's density, if we can treat it as constant. In the atmosphere, we can treat it as constant in many cases. And so the question we're going to answer today is, how high can we get in the atmosphere before we have to really take into account the fact that the density is not truly constant? As you go way up in the atmosphere, of course, you're aware that the density of air will get less and less. And in fact, if you go high enough, you actually go into the vacuum of space. So that density is going to continue to decrease as you go up. But are those density changes significant at the kind of engineering scales that we are working on, and what scales would those be? So we're going to, of course, start with the ideal gas law, P equals rho RT, no problem there. We know that R for air is equal to 0.287 kilojoules per kilogram Kelvin. P naught we'll take, of course, as 1 atmosphere, which is equal to 101,000 newtons per meter squared. So that's where we have standard atmospheric pressure doing the planet Earth here. Let's pick a temperature. We're going to let T equal, again, standard temperature. We call it 20 degrees C, which is equal to 293 Kelvin. So we have those conditions for our air, standard atmospheric situation. And we want to find an H such that the density will be changed by 1%. So let's see how high we have to go. How high do we have to go into the air? Do we have to go for rho to equal 0.99 of rho at at ground level? And you can see from the ideal gas law that that's just directly related to the pressure. So the temperature, we're saying, is not going to change. Obviously, R is not going to change. So the only things that are changing are P and rho. So if we're talking about having a 0.99 rho, we're talking about having a 0.99 P. So the question we're asking then is also, so where is P equal to P naught times 0.99? So that's how we're going to go about assessing this. So we're going to try to find a height at which the atmospheric pressure is decreased by 1%. We're going to do this first by treating rho as constant, and then we'll check to see, if that's okay. So equals constant, because we've just said actually that if we are within 99% of Earth atmosphere, standard atmosphere, then we'll be within 99% of density as well for the air. So we know that that rho is functionally constant over this region, and that's why we're interested in it. So minus rho GH is going to be our formula. So that's the height, the pressure at any given height is going to be equal to atmospheric pressure minus rho GH, where H is how high we've gone. And that's from the prior formula that we've been using. So now we're going to say, all right, let's find out what rho is at that first initial condition. So we need to find rho. So we need to find this. We're treating rho as constant. So we're going to find rho at that standard atmospheric pressure. So back to the ideal gas law. We have P over, of course, RT here. And that's equal to 101,000 newtons per meter squared. That's our pressure. And then I'm going to divide that by 0.287 kilojoules, kilograms, and Kelvin, and multiply that by 293 Kelvin. So this is a very common calculation, and it's a very common mistake because these units do not match. So very important right here. You saw this in thermo. Hopefully you corrected it in thermo. But that unit and that unit do not match. Units do not match. because this is newtons per meter squared and this is kilojoules. So the kilograms are okay because that's the newtons include kilograms meters per second squared. So kilograms are the standard SI unit. But kilojoules are not the standard SI unit. The standard SI unit is the joule, which is the newton, newtons and meters. So we're not going to have kilojoules here. We're going to have to turn that into joules if you wanted to do this. So if you wanted to write it out, it would be 101,000 newtons per meter squared, then 287 joules per kilogram per Kelvin, and then 293 Kelvin. And if you do that all right, you find that the density of air under standard conditions of 1 atmosphere and 20 degrees Celsius is equal to 1.2 kilograms per meter cubed. And I had encouraged you to try to remember roughly what the density of air is under standard atmospheric conditions. It's around 1.2, 1.25. So hopefully if you had made this error, you obviously would have had a density that would have been about 1,200 kilograms per meter cubed. Hopefully you would realize that that's just simply ridiculous. Water is 1,000 kilograms per meter cubed. Air is certainly not nearly as dense as water. So we're gonna go with the correct one here, making sure our units match. We get 1.2 kilograms per meter cubed is our density of air. So now we can go ahead and plug that back into this formula up here. So we have our density for that. So we have that the pressure at some height h is equal to, P naught, or I'll just say, we'll just say P naught. Minus P naught is equal to minus, now my density, 1.2 kilograms per meter cubed, times gravity, 9.81 meters per second squared, and then times H, which is what I'm actually seeking. The pressure that I'm looking for is 0.99 P naught. So I have 0.99 P naught equals P naught minus P naught is equal to minus 11,772 kilograms meters squared second squared H. So then I can obviously divide out the P naught. I get P naught times negative 0.01 is equal to minus 11,772 kilograms meters squared second squared H. Obviously my P naught, I'm going to put that in units now. So I'm going to go ahead and say that's 101,000 newtons per meter squared times negative 0.01 is equal to negative 11.772 kilograms meters squared second squared H. All right, so then this is just algebra at this point. I'm going to rearrange this. So we have the H is equal to 1010 newtons per meter squared divided by 11.772 kilograms meters squared second squared. And finally, you get H is equal to 85.7 meters. So you can go, 100 meters into the air, and roughly a little less than 100, 85.7 meters in the air before the density of air changes by even 1%. So for any lab scale problem, we can treat rho air as being approximately constant for hydrostatics. So if the flow is not moving, you can say that the air density is pretty much static as long as you're dealing with height differences that are of 100 meters or less.